Edexcel Decision 1, Linear Programming 3, using the Simplex method. Interpreting the Simplex tableau. So in our previous video, we looked at applying the Simplex algorithm to this linear programming problem, and this was our initial tableau. So it's important that you are able to interpret a tableau initially and after every iteration. So basic variables are non-zero variables, and to find these we look for columns with a single 1 and lots of zeros. So in this case we've got S1, S2 and S3. So S1, S2 and S3 are basic variables and everything else are non-basic variables. So non-basic variables are equal to 0. So that means from our table we can see that S1 must therefore be 12 since X and Y are 0. We can see that S2 must be 30 since X and Y are 0, and S3 must be 20 again because X and Y are 0. And therefore this means our objective function is also 0 since X and Y are 0. The tableau relates to the starting point, which is at the origin on our graphical solution, and obviously at the origin X and Y both equal 0. Okay, so after our first iteration of the Simplex algorithm, we got this table here. So this table gives us a valid solution, but it's not the optimal solution since the objective row has a negative value. So as we saw before, we know that our basic variables are variables that have a 1 in their column with lots of zeros. So in this case, X, S1 and S2. So if we look at X, we can see that X must equal the right hand side, which is 10 at this stage. S1 must equal 2. And S2 must equal 10. So our non-basic variables are the other variables. So Y is non-basic, so Y is 0. And S3 is non-basic, so S3 is 0. So this means that the objective function P, which was 10x plus 9y, must be 100 at this stage. Now this stage of the algorithm represents the solution at this point on the graph. So at this point of the graph, we know it has a coordinate of 10, 0. So the algorithm has moved from the origin to this vertex. But it is not the optimal vertex, so now it's going to improve its solution by doing another iteration. So here we have the final iteration, and we know it's the final iteration because the objective row has no negative elements. So to find the basic variables, we look down the columns and we find columns that have a single 1 and lots of zeros. So that's X, Y and S2 in this case. So the basic variables are X and Y and S2. So the non-basic variables are S1, which must be 0, and S3, which must be 0. So we read off the values of X using the right hand side column. So if X is in row 3, X must be 8. So Y is in row 1, so it must be 4. And S2 must have a value of 2. So this solution tells us that we have moved from this vertex down here up to the coordinate 8, 4, which is here, and this relates to a objective function p of 8 times 10 plus 9 times 4, which is 116, and we know from previous videos that this is our optimal solution. So in summary, the simplex method can be applied by hand to solve problems with more than 2 variables, unlike the graphical solution. Each iteration does give a valid solution, but it might not be optimal, and it sometimes requires several iterations to get the optimal solution. So in the last example, we required 2 iterations. The optimal solution has been reached when there are no negative values left in the objective row. And don't forget, the objective row is always the bottom row. It's important to be able to interpret the algorithm at the end of every intermediate iteration, as seen in this video. So it can be long-winded to do the simplex algorithm by hand, but it's very easy to program, and there's lots of linear programming solver software that does this for us. So our next session looks at using the simplex method.